Okay, good evening. Today we would like to discuss on the fluid mechanics, that is the continuity versions of the topic on the equation of continuity or Abelian continuity equation they can call. What we know that about the continuity equation, mass should be conserved, means mass should neither be destroyed, mass neither should be created, means neither it should be created nor it should be destroyed, means there may be a possibility to have the conversion from one phase to another phase. For example, liquid water may get converted into the water vapor, or liquid water may get also converted into the ice, that is the solid ice. There is a possibility that the matter or material may have the conversion from one phase to the another phase in an appropriate situation and in an appropriate conditions. Fluid mechanics also deals with the equation of continuity in such a way that whatever the total quantity is there, that total quantity should be conserved by taking it into consideration of the conversion from one to the other. Let us have the same picture of having a cup of water from a bottle, or maybe solving in waves, solving the dynamics which are generated, which are caused in huge oceans or maybe bigger oceans. Let us see the next one. Let us see that equation of continuity is the fourth topic in your curricula. Okay, I'll try to satisfy, I will try to convince you in some manner by getting any good examples, particularly from the atmospheric dynamics. Wow. See that this diagram. See, looks like a cone for you. Of course, it's cone only. The lower part is with the surface near to the surface of the earth, or maybe few meters above the surface of the earth, and upper distribution is even to the extent of about few hundred meters or even kilometers to a great extent. This is the example of a photography of a more complicated flows which are occurring in tornadoes, cyclones, hurricanes, typhoons. You might have heard the name actually. Means the names are different mainly because cyclone is the one, the system which is generated in the atmosphere due to the rotation of the air mass. The same thing what we are getting in whirlpool in huge lakes or rivers, not in ocean. Okay, whirlpools are appearing in such a way that what we can call in Kannada as a surali, people who enter into that whirlpool will never come out of it. Means once if they enter from here, assume that this will happen in the same case. This is the bottom of the reverse, and this is the top. Once they enter, actually, it takes its own time to reach the bottom, and it will not keep there. Immediately, it will be coming in an anti-clockwise. It will be thrown out either from left to right or right to the left. Thing is that people who are entering into the whirlpool should have a capability to breathe the air for few minutes, sometimes few tens of minutes to few tens of minutes, few minutes to few tens of minutes of that kind. If you go with the oxygen, an external supply of the oxygen, certainly you can enter the whirlpool, and you can see that the convections which are possible and also the flows which are as possible. Here, there is no difference between a whirlpool in lakes or reservoirs to a great extent to that of cyclones. Cyclones are of the same thing spherical, but thing is that the wind speed differs. Cyclones to the typhoons. So cyclones will happen in India or surrounding India. Typhoons will happen in Japan. Tornadoes and hurricanes will happen in the mid-latitude stations like in Western countries like America. Means here the example for the fluid dynamics is because the bottom is very narrow, about a 2 to 2.5 meter radius. Okay, so radius I'm saying, sir, even diameter actually 2 to 2.5 diameter. But the upper one, several hundred meters means the huge systems will be devastated. If once any such type of an waves comes, actually, they will uproot the trees and the buildings will collapse. Means how a differential equations of a fluid motion are employed by making use of the concepts in fluid dynamics one should understand. This is the basis actually. Means to say there should be a conservation of mass. The conservation of the mass is achieved by an equation known as the continuity equation, or you can also call it as an equation of continuity. Means from by making use of the Newton's second law of motion, that is the momentum gets conserved. Rate of change of momentum dp by dt gives you something. Okay, is dealt by two great scientists, the Navier and Stokes. Navier worked for the experimental part of it, and Stokes worked for the theoretical part of it. Both together, there are equations known as a set of equations known as Navier-Stokes equations. Those equations are of great importance in fluid dynamics. These equations, this means that is Navier equations, apply to every point in the flow field. Flow field means either at here or here, here, wherever you go, either left, right, top, bottom, everything need not be for the big systems like this. Wherever you go with the fluid dynamics, that should be dealt by them. Means this enables us to solve for all details of the flow everywhere in the fluid domain. These differential equations are the differential equations which are employed are difficult to solve, and therefore they require the support of a computer. Computer is nothing but doing a task of iterations, doing a multiple task of the solving several things without a distance. These equations must be combined when necessary with an additional equations also, such as an equation of state, equation of the energy, equation for the matter, and special emphasis to the transport of air mass from one point to the another point. Therefore, fundamental differential equations are derived, or maybe a fundamental differential equation is derived from simple flows which can flow in a pipeline, which can flow in a river, which can have the flow in a canal, which can have the flow in a tubular activity. More complicated flows, for example, tornadoes, which is shown, cannot be solved exactly. That we have to depend on the computer. Okay, no issue. What you are seeing? Good. I hope you can able to see it. Both top face, bottom face. Our intention is to write the fluid dynamics for this type of an equation or maybe fluid equation. It is a drop. I will run a small clipping. Wow. See, this is a big obstacle going up. Can we have an equation or differential equation in such a way to replicate this type of a phenomena from the models? Tough task. It's not an easy job. For this kind of a complexity, one has to solve the several differential equations of different kind or different nature. How many of you are from Bidadi? I hope. Some of you are from Ramnagara. Some of you are from Ramohalli, near to our Bangalore University, hardly about some 10 to 12 kilometers from this place. This is known as, this is the dish antenna. What you are having an antennas in your house to get a cable network, TV connectivity, or even cable network also. Not cable network. Cable network will work in a different fashion actually. This is a huge dish of 32-meter diameter. Diameter is 32-meter diameter. IDSN, Indian Deep Space Network, is a complex which comprises of deep space antennas of about 32-meter. This is used to study the interplanetary missions. If you send a satellite to the Mars, send a satellite to the Venus, send a satellite to the Jupiter, Saturn, Moon, okay, where we have to get the signal from satellites. Those signals should be received by the antenna. This is the antenna. This is not a normal kind of an antenna, what you are looking for that, but structure-wise, appearance-wise, it looks similar. It looks a simpler dish what you are using it for your normal antennas for getting the signals for your TV. This is an earth-bound scientific mission. You can control those satellites by giving the commands from the earth. You can receive the signal and also. This is a 30-meter fully steerable antenna. You can drive it. I don't know whether you, with beam waveguide operating in an either S band or X band, don't go with specifications. It is very difficult for us to even to drive two-wheeler perfectly, four-wheeler perfectly on a road if there are wind, if there are rain, if there is a rain, or if there is some kind of disturbances apart from the traffic in a zigzag manner. Means to steer, to guide this type of an antennas it requires. Why? Because there are 18-meter fully steerable antennas for international deep space missions are also available. This 32-meter antenna it is an indigenously realized. Indigenously means it was prepared by the scientific committee from India, and it was prepared. It was entire thing was hosted by Electronic Corporation of India Limited, ECIL from Hyderabad. It consists of a servo system which it takes its own decisions and a precise antenna pointing and tracking with a speed as low as 0.1 millidegrees per second. The cryogenic, that is the cooled low noise amplifiers were used here to make it capable of receiving the extremely weak signals from the satellites. You have to visit and see once. From outside, there is no tough task. You can go for what they can call big banyan tree near Ramohalli. That is also available. See, you can able to see it actually. Of course, through internet also you can see. But if you are having a chance to go there, it is better. Maybe if time permits, we have to make a visit to this station once actually. If you are interested, that I don't know. That you have to respond to me later. This is another. See the same case now. How many of you are there? Maybe 35, no issue. How many of you are aware of swimming in water? Maybe some percentage I can take. Maybe all of you, 100% if you know the swim better. We are good. Of course, I am not a good swimmer. Of course, I am not at all a swimmer at all. If you know swimming, you can swim along the flow of water, maybe in river or maybe a canal, no issue. Even wells, it's a tough task, but still. If you want to go against the flow, you have to put more energy. Now, think that, can you walk in a lake against the river? Can you walk in a river against the flow? It is difficult. Can you keep anything obstacles against the flow of the water? It will collapse. If wind is coming from left and hitting this entire 32-meter diameter, if you work out with the circumference, pi times d, 2 pi r or pi times d actually, 3 times or 32 times 32 into minimum pi, that is the pi r or pi d you can call. Pi means about 3, almost 100 times. 100 meters is the circumference. 100 meters is the circumference. Can you withhold that time? The technology has to develop in such a way, it has to withstand such a huge power. You might have seen that several dishes might have flown up or down during the wind. Several towers might have fallen down. Several trees might have fell down. Several slabs might have uprooted. Sometimes, due to that, several trees and even the electric poles might have uprooted. But thing is that such a type of a dish has to withstand. It is not an easy job. 32 meter and above that about another 10 to 20 meter of that kind, 50 to 40 meter height actually. Height, a huge tower. It sustains. Thing is that they worked out well by calculating all kind of restrictions which are coming from whichever may be the direction to sustain the wind flow. Now, there are two things to understand here. One is the control volume technique, and another one is the differential analysis. We are coming to the deeper and deeper. I spent good amount of time in convincing you by bringing the basics of fluid dynamics in all respects, even though you are well aware of it. But the control volume is that here you can see here on the left, right, okay, top right of that one. This is the structure what I have shown here. Okay, flow is coming here, and the top flow goes very easily. Okay, and here the flow which is out. This is the flow out from all the directions. Okay, control volume is the entire unit, how the fluid behaves for the system. Control volume technique is useful when we are interested in the overall features of the flow, such as mass flow, entire thing, right? Mass flow rate into the system and out of the control volume, or net forces which are applied to the body. How much inflow is coming, how much outflow is there, what is the loss behind it, total flow across the volume unit. This differential analysis involves, or differential analysis by making use of the differential equations involves applications of differential equations of fluid motion to any and every point in flow field over a region, and it is called the flow domain. This entire thing is called the flow domain. Here you can see that here I have shown that if it is for entire thing, how much it is coming in, how much it is going out. It is flow in and flow out, what should be the net. Okay, but differential analysis shows in such a way that flow domain is in such a way, see that this is coming here, going up and taking a turn, maybe getting inverted. Here, nothing is allowed here inside actually. Some wind may come and go like this, here encircling, okay? But something is coming and going like this. Yeah, definitely possibility is there of that kind actually. Means one has to have the boundary conditions. Boundary conditions for the variables must be specified at all boundaries of a flow domain, including what must be the inlet, what must be the outlet, and what should be the periphery or the walls. If the flow is not steady, not streamlined, they can call, we must march or move our solution along in time as flow field changes. Means to say that the one here, whatever I have shown is that in a control volume analysis, the interior of the control volume is treated as like a black box. We don't know, we don't want, we are not interested in that. But in a differential analysis, all the details of the flow are solved at every point within the flow. That is why if we expect here, the wind which is coming here also may hit actually. Here may coming hit. It may come from left, right to left, and even for the ferry. Something which is coming going and up, also shoot up. Means in a flow, air density and temperature changes are insignificant. We are not considering. Means there is a change in the density of the air. To some extent, it is allowed, and the change, very infinitesimal change. If it changes drastically, we have to take it to the account. But it is sufficient to solve two differential equations of motion. One is the conservation of the mass, and another one is the linear momentum equation. But the linear momentum equation can be solved by the virtue of the application of Newton's second law. For three-dimensional incompressible flow, that is like fluid, water, there are four unknown quantities. What are those four unknown quantities? Particularly three velocity components. One is along the direction u, and another one perpendicular to that direction v, and this is w is the vertically upward towards east. For example, along the rotation of the earth, if you take east is u, along the north is the v component, vertically height is w component, and also a pressure. Means four unknown quantities plus the four equations are required to solve these four unknowns. One from conservation of energy, which is a scalar equation, and three from the Newton's second law, which is a vector equation. Newton's second law, rate of change of dp by dt gives you the vector quantity. The equations which are coupled here, meaning that sum of the variables appear in all four equations. The set of differential equations must therefore be solved simultaneously for all four unknown conditions. Means to say that in addition to that, the boundary conditions for the variables must be specified at all boundaries of the flow domain, including the inlet, outlet, and walls, because we should have some velocity component along east, some velocity component along north, some velocity component along the height w direction. Means to say that for any unsteady flows, the solution is along in time and also along in time as the flow field changes. Means to say that observe here how differential analysis of fluid flow can become quite complicated and is difficult to solve. Means to say that, but computer plays an important role, also a tremendous role in the computation of all these put together with the aid of numerical techniques, what we are away from earlier paper in solving the differential equations. Either you can go for the Euler method, or you can go for the Runge-Kutta method, or you can go for the whichever method you want. Actually. Simple, don't get scary. This is what we require for the conservation of the mass or the continuity equation. Let us choose here. This is the volume, control volume. Z1, X1, Y1, along the X, along the Y, along the Z. This always you will say that consider an infinitesimally very small box, dx, dy height, and dz of that kind. Y is the height actually. Okay, this is a box. Okay, volume is that Z times X times Y. It has to be given. X, Y, Z. You can X is along the direction, Y is perpendicular Z. What it is said that conservation of the mass for a continuous volume is written in such a way that rate of change of density with time, that is particularly partial with the time, rate of change of density with the time within the control volume of dV, as in a continuous volume CV, plus rate of change of this V dot dA, area also gets changed. How much it is there, that one should know. That should be equal to 0. It should be conserved. Means this equation is valid for both fixed and moving control volumes, provided that velocity vector here, Velocity vector is the absolute velocity. We should be know. It means it moves with some speed as seen by a fixed observer. When there are well-defined inlets and outlets, what will happen? Rate of change of density with the time, this is the in, should be equal to, for the total volume should be equal to the mass which is flowing in minus mass which is flowing out. Means the summation of mass which is coming in from all the direction, the summation of all the masses which are exit out. For example, for overhead tank, you may be supplying the water by pumping from the reservoirs. You know that what must be the flow rate. See, if the flow inlet exceeds the outlet, certainly flow should dash. If outlet will never exceed the inlet, your tank becomes empty. If inlet and outlet gets matches at some time, then you can't expect that whatever the level of water is there, the same level will be maintained. Now, the rate of change of mass here, rate of change of mass within the control volume is equal to the rate at which the mass flows into the control system minus the rate at which the mass flows out of the control volume. Assume that I am sending 10 liters per minute to an inlet and the same 10 liters per minute as an outlet, the reservoir remains constant. You might have witnessed in the media while telling the height of reservoirs every day, the inflow is quite high. They have to release the water to a great extent. Before it gets filled up, they used to say that, oh, now it is picking up. The level of the reservoir is day by day is increasing. Once it reaches some critical height, or once it becomes few feet or few meters above the threshold for fulfilling, otherwise the reservoirs can't withhold such type of pressure caused by huge or hectic water. Okay, what normally they will do? They will release the water in the canals. Those that may, if some people are constructing the houses in the backwaters, okay, or maybe the watersheds actually, that may be collapsed or maybe drowned actually. It should not happen. Okay, means if you know the inlet, if you know the inflow, and if you know the outflow, certainly you can estimate that what must be the net. Means to say, to generate the differential equations of this kind, del rho by del T equation, for conservation of the mass, we imagine the control volume is shrinking to infinitesimal size. See here, it is sinking to the infinitesimal size with the dimensions of dx, dy, dz. In the limit of the entire control volume shrinks to a point in the flow. Means it is a huge system, it gets shrunk to the smaller dimension. Maybe you can say that 10,000 cubic meters may be converted to the few cubic meters of that kind. That's right. Okay, it is a related terminology. What will happen? See that. One can derive this using the divergence theorem. If they ask for the continuity equation, write this equation and explain this diagram. That is good enough for 5 to 6 marks. How one can go for the derivations of this kind? The quickest and the most straightforward way to derive the differential form of conservation of mass is to apply the divergence theorem. Divergence theorem is also known as the Gauss theorem. The divergence theorem allows us to transform a volume integral, divergence of G, volume integral of the divergence of a vector into an area integral, surface integral they can call. Volume integral gets converted to the surface integral over the surface. That defines the Gauss theorem or divergence theorem. You are aware, you take this relationship which is mentioned in the red in color and explain. For a vector quantity like G, the divergence of G is defined as the del dot G, and the divergence theorem can be mentioned in red color. Means to say that the circle on the area integral is used to emphasize that integral must be evaluated around the entire closed surface, closed area that A surrounds, which is the volume of V. Also, you can call it as G is equal to rho times V. G should be equal to rho times V. Here you can write del rho by del T times dV plus continuous volume del dot rho V of V. Or you can bring them together within the integral. Okay, del rho by del T plus del dot of rho V must be equal to 0. Means finally, what happens? This equation must hold for any control volume regardless of its size and shape. This is possible only if we integrate the terms within the square bracket here. If we integrate it, actually, is identically equal to 0. If you integrate it, what will happen? This value should be equal to 0. Del rho by del t plus del dot of rho v must be equal to 0. Hence, we have a general differential equation for the conservation of mass. It is better known as the conservation of mass is better known as the continuity equation. What happens here? The divergence theorem states that the surface integral here, surface integral of a vector field over a closed surface, which is called the flux through the surface. Flux through the surface is equal to the volume integral of divergence over the region inside the surface. In 2 dimension, it is equivalent to the Green's theorem. Therefore, this equation is compressible form of the continuity equation. Whatever red color it is shown actually, since we have not assumed the incompressible flow. It is valid at any point in the flow domain. You see that left face, right face, bottom face, top face, front face, rear face. There are 6 faces. One is from left, another is from right, from top, from bottom, from front, from rear ends. There are 6 faces. Here I am trying to say that I don't know, someone could not able to get you the thing. What I will do here, if you expect here, sorry. This is the cube. How many faces are? 1 face, 2nd face, 3rd face, 4th face, 5th face, 6th face. Yes, there are totally 6 faces. Like that. Just I thought of showing you, and it is how it is appearing for you actually. Are you able to see screen round still? At least one confirmation, please.
Yes, sir.
Okay. Now he can derive this using the infinitesimal control volume. The same thing. There is no much confusion here. Take the box dx times dy times dz. Let us put this point P at the exactly center. Halfway from the left side, right side, halfway from the left, halfway from the top, and halfway from the middle, halfway from the front, halfway from the face cubic body cubic center, BCC, what you can call. Those who are from condensed matter physics are well aware of it actually. This is body cubic center. It is a cube actually. Body cubic center, body cubic center. We derive the equation, continuity equation in a different way by starting with a control volume on which we apply the conservation of mass. What will happen? Consider an infinitesimal box which is shaped box shape control volume aligned with the axis in Cartesian coordinates, for example, dimension of dx, dy, and dz. All the centers of this box, for example, the density rho is defined, and with the velocity u along the x, y, v along y, and w along the z. Okay. At any point or at any location away from the center of the box, you can use the Taylor series expansion about the center of the box, particularly from point P. You can see that u, v, and w. In earlier P101, 401, I explained you the Taylor series. Rho times u plus del by del x of rho u times dx by 2 plus 1 over 2 factorial del square by del x square times rho u del x by del x by 2 whole square. Like that, the expansion can go. What it says is that a small box. Here, the red color indicates the center of each face. This is the center. This point is the center. The top center. This is the for right case. This is for left. This is for the bottom. This is for the front actually. Okay, there are 6 faces. 6 are there. As box representing the control volume, which shrinks to a point, maybe a second order differential equations, and higher terms are neglected. If the rate dx by L is of the order of 10 to the power of -3, L is the characteristic length scale of the domain, then dx by L, how much it should be? 10 to the power of minus 6. Compared to the minus 3, if you take for 10 to the power, second order, it becomes 10 to the power of minus 6, a factor of almost 1000 times less than the dx by L. Means to say, if the dx is very small, the better the assumption. That is, the second order terms are negligible. Applying this to a truncated Taylor series of expansion to the density times the normal velocity component at the center point of each of the 6 phases of box, one can solve the differential equation. How it will happen? See that rho times u at the center of the right phase, for example, should be rho times u plus del by del x of rho u dx by dt, because you are taking from the first half. If it is negative, here minus of dx by dt. If it is from the top, plus rho times w plus del by del z times dz by 2. If it is at the bottom, minus dz, because the reference point is p. If it is from y side, that is other path, why here going up actually? Why here going up actually towards positive y axis, and this is for negative y axis. How many are there? 1, 2, 3, 4, 5, and 6 actually. Being this 6, this is 6. This phase is represented by rho v time plus del by del y of rho v dy by 2 of that value plus dx, sorry, into dx by dz for the surface area. This was this phase for dy by dz. The bottom phase for the negative. The negative side left is for the negative value, and this for the front face with the w. This is the rear face with the w. Means to say, if you take the surface area Pn, the vector quantity normal to that surface area, average normal velocity component, what will happen? The mass flow rate into or out of one of the phase is equal to the density times the normal velocity component at the center point. Means to say, m is equal to rho times the same equation Vna at each phase. If that is the case, rate of change of mass within the control volume should be rate of change of mass. d rho by dt should be proportional to del rho by del t times dx dy dz. Okay. Here, net mass flow, how you expect? The summation of all of them put together. This is for the left face, left. This is for the bottom face. This is for the rear face. Left, bottom, rear, that is back. If you go for the next ratio, net mass should be right face, top face, front face. All 6 faces are over. Now, you have to take this one. Del rho by del t, del rho by del t, dx, del rho by dt, dx dy dz must be equal to, you add all of them, this gets cancelled actually, one terms, minus of del by del x of rho u, dx dy dz, minus del by del y of the same case. Means to say that the volume of the box dx dy z appears in each term and can be eliminated. This dx dy dz actually, it is a common. After with the rearrangements, what you will get? Del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w must be equal to 0. In the compression, this is the compressible form of continuity equation in Cartesian coordinates. It is also written in more compact form by recognizing the divergence which is shown here. Del dot rho times v, you can enlarge it into the Cartesian to the cylinder also. Both versions are available. You can restrict up to this extent for the continuity equation. Let us take from this phase, then correct this. These are the same thing actually. Go with this equation and come for this, then finally arrive for this equation. This is the derivation or expression for the continuity equation. For further understanding, you can use the examples. I will share you right now. Maybe you read the problems. Okay, just I quoted with you some of the textbook. Actually, I will share you later also. An air fuel mixture is compressed by a piston in a cylinder of an internal combustion engine. Then one has to estimate that how much is the fuel and air being compressed by a piston in a cylinder of an internal combustion engine. How that changes, one has to work it out. This is the cylinder. This is the piston which is working. From time t is equal to 0 to time t, how much the pressure it can build up. Analysis, it has to go with the velocity component, the same equations. Okay, I will leave to you. Okay, solve for this, you can obtain the expression like that. Means how that can build up non-dimensional density as a function of non-dimensional time, for example, has to go with the equation of this kind actually. Means rho by rho naught, you can build up like that actually. Here one can work it out what must be the possible time for that. You can have the design of a compressible convergent duct. Fluid moves like this. What should be the equation? See that the same conservation of mass. The value of the psi increases if you go like that. 6, 7, 8. Observe here it is 5 is there, 6 is there, 7 is there. See that it is going like this. It is going like this. It is going like this. Maybe relative velocity will be deduced from the streamlines. If something is flowing in flow, if you are having something like that here, it abstracts. Volume flow rate can be reduced from the streamlines. See that these are equations. These are the examples. Looks like a complicated for you, but just see that at least you work out with the rest of that part. Differential analysis of flow problems can occur. There are two types of problems, maybe continuity and Navier-Stokes equations. This I will take it up in next class. I don't know how much time I'm having. See that? See this? Don't scared about the information, additional information what I am providing. Finally, the two-dimensional, what I shown earlier, the two-dimensional line vortex is a simple approximation of a tornado. It comes, moves like that. P should be like that. Change in the pressure gradient like that. P infinity it has to go. Pressure will build up. See that? This is how it has to go. One has to sustain. After reaching that, it will come back. See, going, coming, going, and then gets reversed. I'll stop at this moment for you. No class for tomorrow. And if there are any questions, I feel happy to answer to your ask.